Welcome to ECE 320A, and this is the review session for exam number 2. The process for exam number 2, just to be clear, you do get one more sheet of notes, and that can be front and back. But if you want to include Laplace transform pairs, you need to create those or put those on. You can copy them, you can paste them, you can do whatever you want to get those, but I'm not furnishing you with any tables. You use the table that you're comfortable with and put it on your 2 sheets of notes. Is that clear? You can bring a graphing calculator even if it's brand new. Something to write with, obviously, but there's no textbook, no cell phone, no class notes, and no computer. That should be clear from the past. In terms of material, here is a list, and there is a list of topics that's maybe a little bit more verbose than what this is. This is a little more concise or to the point. You need to be able to write or find integral differential equations for an RLC circuit. You need to be able to establish initial conditions, and if you see this somewhere or maybe in a job interview and somebody goes, "Can you put a choke in that circuit?" You're going, "What?" That's an inductor. So have you ever heard of it as a choke? Okay, so now you have. Now if somebody starts talking about a choke, you know it's just choking off high frequencies, and that's what an inductor does. Or you could have capacitors, but you need to know how to find their conditions. And initial condition, if it's been in this state from minus infinity up to 0, it's in steady state. So you're doing a steady state problem prior to t equals 0 to find or to determine the capacitor voltages and the inductor currents, where your chokes or inductors are shorts and your capacitors are open. And now you can just do some DC analysis to find those initial conditions. Is it clear if I ask you for the structure of a solution? If I ask for the structure, I don't need you to find the partial fraction expansion coefficients. Now you're mad that you bought that calculator. But if now I just want you to find the roots and use those to determine the structure of your solution. These could be exponentially damped sines and cosines. They could be exponentially damped expressions. They could be impulses. They could be derivative of impulses. But those will just have arbitrary coefficients associated with them. That's what I mean by structure. And if you had a differential equation and you were given initial conditions, you need to be able to put those in to the expression. And when do those come into play? When do you see initial conditions? When you're Laplace transforming derivatives. When you Laplace transform derivatives, then these initial conditions start appearing in your expression. So you need to be able to Laplace transform differential equations. You need to be able to go back and forth by inverse Laplace transforming or Laplace transforming. You need to be able to do partial fraction expansion with distinct roots, either real or repeated, and repeated roots with real or repeated, and a table, and there's others. But someone was asking before we got started, how do you do this when you have repeated complex roots? Maybe they didn't have a problem finding the k, but this is the last row when you have 2. roots that are on top of each other that are complex. Now you know the expression to go back and forth between the time domain and the frequency domain. This is table 12.3. But now I think the question was, well, how do I find the coefficient above the unsquared factor? And there you might want to find two convenient values of s, and you now have two equations and two unknowns to solve for. You don't always have just one convenient value. And when I say convenient value, what does that mean you need to avoid? You need to avoid values of s that cause your denominator to go to 0. Those are the poles. You can't be plugging in poles for your values of s for a convenient value. Then you get infinity equals infinity, which is true, but it doesn't tell you anything. It doesn't allow you to isolate or identify your coefficients that you're wanting to identify. But that's 12.3. Actually, if you want to know maybe an equation that's more than just squared, then you should look at equation 1283. This is for real and repeated, and that's for any repeated up to Nevada n times, or the next equation in the textbook, equation 84 in chapter 8, and this is for complex repeated. And you might want to put that on your notes, on your sheet of notes. You don't have to have that memorized. You can just use that expression. You will have to find all of the coefficients, the A1, A2, A3, A4, if it was s plus something to the fourth. And you would have to use more than just one convenient value if you were using that approach. You could do a common denominator, and then you get 4 equations in the 4 unknowns. That's partial fraction expansion. You need to be able to deal with poles and zeros, know what those are and how to find them. The zeros are the top. Those are the numerator. Those are the values of s that cause the top or the numerator to vanish or equal 0. And the poles, if those are 0, the whole thing is blowing up. That's why they're called poles, because it makes the whole thing go unbounded. But the denominator equaling 0 are your poles. And then you need to be able to apply the final value theorem and the initial value theorem. How do you know that they are valid, these theorems? The initial value theorem, when can you apply that? Or when is it okay to use the initial value theorem? All you have to know is that that limit on the right exists. If that limit exists on the right for the initial value theorem, you can apply it. That's not the case for the final value theorem. The final value theorem, you have to look at the poles of s times capital X of s, and if those are all where? If they're all in the left half plane, then you can apply the final value theorem. If it's on the axis, which axis? You're showing me the real axis. If it's on the real axis, if it's in the left half plane, you're okay. If it's on the imaginary axis, no, 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 no. It has to be in the strict left half plane. It can't be on the axis. What happens if you have poles on the axis? What kind of a behavior? It just shakes forever, doesn't it? It's an oscillator. There's no decay. So that's more than I wanted to spend on this. But are there questions on the topics? Is it clear what I'm asking you? And this is maybe not an exhaustive list, But essentially chapter 12, and maybe knowing how to deal with poles and zeros, transfer functions, that's maybe some of that from chapter 13, but don't worry too much about the 13 stuff. Maybe I was getting a little bit ahead of myself when I assigned those problems, but we'll get there for the next exam. But all you needed to know was really how to generalize this idea of an impedance. The impedance of an inductor is SL. The impedance of a capacitor is 1 over SC. The impedance of a resistor, R. And now you can just play with those impedances just like they were R's, except now they have S's floating around in them, and you can derive relationships for those impedances. Other questions? It was nice seeing you. Yes, sir. Oh, now you're asking for the impossible. I think you were asking for table 12.3, and can you see it now? Sorry. Which one were you interested in? How do you know the sine of the angle? Now, I think buried in that question is the key question that I kept trying to emphasize, but until you start getting the answer wrong, you don't know what I'm talking about, or you don't care what I'm talking about. What I'm talking about now is if we go back to this, let me zoom back a little, and if you now have the following complex poles, and let's say this is at minus 2, J3, and this is at minus 2, minus J3. You know that the structure of your answer in the frequency domain is you have two terms. One of the, if you do it with distinct roots, you now have S plus 2 minus J3, and that's a K, plus S plus 2 plus J3, and this is actually K star. Now, which pole does this correspond to? It's the value of S corresponding to this one in the second quadrant that causes that factor to vanish. If you plug in S equal minus 2 plus J3, that denominator vanishes or equals 0. That's the K that you need. When you start using these formulas, they're assuming that you set it up to have K on top of the pole in the second quadrant, and K star is on top of the pole in the third quadrant. And that should give you your correct sign on your angle. Pardon? So that's the information that you have to keep clear, is when you are trying to now find this partial fraction expansion for complex roots, you need to put your coefficients K that you're solving for on top of the pole factor associated with the pole in the second quadrant. Yes? So you don't have to rederive what I derived in class. I think the question was if you find K, if you know K, and K is a complex number, it's a magnitude and an angle, then you can immediately use this invisible formula. You can now use row 3 in table 12.3 to go into the time domain expression. You just find the magnitude of your partial fraction expansion coefficient, the magnitude of K, scale it by 2, that's coming to you from Euler, because e to the jx plus e to the minus jx over 2, that's where the 2 is coming from in this relationship. And then the angle, that theta, is the angle of your K. And that angle is only going to be correct if you use that second quadrant pole. Did that answer your question? Now, if I just ask for the structure, you can just use this as an unknown K. The magnitude of K and the angle of K, that's theta. You wouldn't have to solve for this complex number K if I just asked for the structure. Question? What if alpha is negative? So now if alpha is negative, then this is going to, what will this do in time? Pardon? It's going to blow up, but you can still use these equations. It's going to be exponentially increasing. It will just now be e to the 7t. It's not e to the minus something t. It will just build, but it will be oscillating as it builds, and you'll probably have to go get another part from the stockroom if in the lab you end up with something with a positive alpha, or in this case, a negative alpha in this formula. If you end up with an e to the 7t, I wouldn't plug in my power supply. I would go, ooh, I better watch this. Well, I won't watch it. I better go back and re-look at my analysis and make sure I'm doing this properly. Question?
So, if you 5 over x plus alpha minus j beta, we're going to find the expression alpha plus j beta.
I didn't hear what you said, so let me write that down as you say it. Just a minute. What did you say we had?
So if our expression is like 5 over x plus alpha minus j beta,
so now you know that this has to come in conjugate pairs, right? So that this is going to be 5 over s minus alpha minus j beta. In this case, because you didn't give me an angle on that 5, this angle is 0, so I'm not going to get the sign of the angle wrong. But if you would have given me an angle, if this would have been 10, this would be minus 10, and which of those would I have to use to get the correct answer? The one on the right. So now I would have something like 5 times 2 e to the alpha t cosine beta t minus 10 degrees. And when is that true? For t greater than or equal to 0. So I'll switch it on with the u of t. Can I scroll up? How big? Does that answer your question? All right. Wow, maybe I need to shuffle this around. Or what do I want? I've got too many options. Why don't we start here? Have you already looked at this? This is one of the practice exams. This is writing an equation for a circuit. This is problem 2, I think, from the fall 2013, exam number 2. And you'll have something like this on your exam. You'll have to write the governing differential equations for probably a second order circuit. Second order means, what does that mean? You have 2 energy storage devices. Yes? Will I ever specify? Probably not. I think I want you to feel comfortable deriving these however you've felt comfortable. If you always like to use KV or mesh equations, then probably you need to use mesh equations. If you like node voltage, use node voltage. What I want you to start getting comfortable with is being able to do either or something else. but you should be able to start solving these problems. Yes?
I just wanted to clarify my understanding what you want as for governing differential equations. It's kind of
Well, there's a debate, and the presidential candidates are governing this equation, and we need to know which way they're leaning. No, it just means what is describing the behavior of this circuit. That's what's governing its behavior. What are the differential equations that will describe the behavior of this circuit? Which means if you have two energy storage devices, you are looking for either one second-order differential equation or two first-order differential equations that are probably coupled. By coupled, I mean some voltages in one or in the other and vice versa, or they might be sharing currents and voltages between them.
okay. That makes a lot of sense. I thought you did separate solutions for this problem, and then in one solution you only had one equation. Yeah.
Yes.
That makes more sense.
So if I might solve this or not tonight one way, but you should go back and look. This is what you're trying to develop your skill set in, and one way might be better than another for you in terms of understanding, but you should understand that they're equivalent, these solutions. You could end up with one second-order differential equation, especially if you use the ladder technique, for example, and you might get V1 and V1 prime and V1 double prime and V. Then that would be your equation. That would be fine. Or you could say, oh, he's got basically node voltages. Maybe I should write a couple of KCL equations. And those are now in terms of V1, V2, and V, and you could write those, and then you would be done. Questions on this? Do you want me to go through this problem? Which way do I want to do it? Who knows? There's all sorts. Which way would you like to see it done? I've done it through. Pardon? You want the ladder? I don't know that we have time for both ways. I would do it the way that seems the cleanest for you. If you were looking at this, what would be that way that you would start? Maybe. KVL, so you would write mesh equations. Okay, I think that's the way that you all kind of like to solve problems. You like to solve mesh equations. This one you might want to do node voltage equations. It's sort of set up that way because of your voltages at the nodes. If you do KVL, then you have to sort of put in the correct current expression in terms of these voltages, because I'm saying write your equation in terms of V1, V2, and I'm not saying any currents. So if you do define mesh currents, you have to rewrite those in terms of V1 and V2 and V. So KCL, node voltage analysis, is probably more appropriate for this problem. Yes? If you wanted it in, so the question was, if I wanted it in terms of just V1 or just V2, then would you want to do ladder? Probably if it's V1 and V, yes. If it's V2, then I might do node voltage and back out or rewrite my equation in terms of or rewrite V1 in terms of V2 and then substitute it out. But I might do that in the frequency domain, because then I'm just doing some algebra in S, and then I would inverse Laplace transform to get my governing differential equation. All right, we're done with this problem, right? Do it? So this is a Nike commercial, just do it? And which Well, I know which one you wanted. You wanted the easiest. So I would... All right, now we are having a debate, aren't we?
I mean, it's really what
Yeah, let's do that.
He wanted a ladder.
I actually did want ladder because I had no idea.
All right, so I don't want to do something that you won't use. I mean, if you like ladder, you can use ladder. I'm just saying and so that's the problem with these problems, is I have to grade 80 of them and they're all different. I'm really looking forward to this weekend, if you couldn't tell. But if you see it as a ladder, solve it as a ladder. If that's not how you work it, if you struggle with it, I wouldn't do a ladder. I would say, let me solve it the way that it seems to work. Yes?
I think our whole concern with ladder is there ever going to be a circuit solved?
No, I don't. The question was, is there going to be a circuit that you can only solve with ladder? No, I think you can always fall back. Pardon? No, I think in general, if you're trying to, here's the benefit of the ladder, is it allows you to find one equation in terms of maybe an output variable in the input source, and you can basically do it in a progression towards the left, and you don't have to invert a huge matrix. You don't have to sort of turn the crank at the end and go, I don't know, I hope I didn't make an algebra mistake. With the ladder, you can follow your analysis as you go, and the logic should sort of make sense. And at the very end, you've just gradually found the entire solution. So it's sort of clean that way. It'll get even cleaner when we leave the time domain and we put this circuit into the frequency domain to begin with. When we convert all the L's to SL's, we convert all the C's to 1 over SC's, and the R's we leave as R's. Then we're dealing with Chapter 13. But that's not Thursday. Thursday is Chapter 12. You do need to... No. So the question was, are we allowed to use Chapter 13 Thursday? And the answer is no. You can, if I ask you for an impedance, use SL and 1 over SC and R. But I don't want you solving this circuit problem in the frequency domain because I'm wanting a differential equation. You can do it, but then you would have to inverse Laplace transform, and I don't want to solve another way of doing it when we haven't officially gotten there. Okay? We'll get there. On the final, you can do it however you want, and that means probably you will all start solving it via Chapter 13 techniques. But now I want you to feel comfortable with Eli and Ice in the time domain. So if we did nodal analysis, here are the two nodes. And you're simply summing algebraically the currents at those nodes. For example, if I label this as A and this is B, if I say KCL at A, I now need to, let's say that I want this current and that current and that current. Those will all sum to 0. The current, horizontal current going to the left, how would you define that in terms of the V's? Well, all the V's. V, V1, and V2. That's the current horizontally going to the left. That wasn't very hard, was it? That's just the voltage drop from right to left across that resistor so that I would get a positive current going to the left if V2 was more positive than V. The signs will take care of themselves, but this is the expression governing that equation. What's the vertical current down through C sub 2? Oh, what did I say? Current or voltage? Current, which we're doing currents, aren't we? So the current down there is ice. That current is C sub 2 V sub 2 prime. And what about the current going to the right, horizontally, out of node A? Positive going to the right. Are we done? You have about 5 of the 10 points, though, and that wasn't very hard, was it? That's one of the governing equations. That was kind of straightforward, I hope, that you're starting to say, hey, this isn't bad. Now, we have just one different, we have basically a first order differential equation, but there's some coupling. We have a V1, a V2, and a V. What about, now we need a second independent equation. We have a second node sitting over there at B. Let's apply KCL at B, and I'll change colors. Now I'm defining my currents to be leaving that node in red. And if I now do a KCL at B, what's the horizontal current going out of B going positive to the left? How would I define that? And that should be the negative of that blue current that I just found earlier. And it is, isn't it? This last term in my first equation, I've just written the negative of. And I now have one more equation for the current leaving node B, and that's the current vertically down from node B, and that's C1, V1 prime. That's just ice. Those two algebraically sum to 0, and you're done. That's it. Those are your two equations. You have two first-order differential equations that are coupled, meaning they're sharing V1s and V2s in the two different equations. If you now wanted an equation for V2 on the final, not for this exam, I would Laplace transform both equations, solve for V2 in terms of V, and then if I wanted the differential equation, I would inverse Laplace transform, and I now have a second order differential equation in terms of V2 and V. Yes? This is how I would want you to leave that final answer. I would box those and say, this is my final answer.
So you would be asking us to take this and Laplace transform.
So the question was, would I be asking you to take this and Laplace transform? I could. You will have to Laplace transform differential equations. I don't know if I will ask you to have, well, I might. I might ask you to find a V sub 1 of t, the solution. Then you would have to, I probably may not do it where you're coupling equations. Now you would have to do this with some algebra, linear algebra. Now you have 2 by 2 matrices with S's floating around, and then you inverse. But it's doable. Your yeah.
Okay, why do we have...
Pardon?
Okay, alright, why is B, like, why are we doing it in the case of...
Why are we doing a KCL at B? So how many equations, first off, you look at this circuit, and how many energy storage devices do you have? 2. What's the order of the circuit that this, or the order of the equation that this circuit represents? Second order. The first equation you had from A only really gave you a first order. You needed another first-order equation to give you all the information, all the governing equations that describe the dynamic behavior of this circuit. So you needed B because you have two independent nodes, and you have two energy storage devices. If it was third order, then you would need, or if you had three energy storage devices, you would need three first order coupled differential equations, or a second order and a first order, but you would need three independent or a third order differential equation. Did that answer your question? So if one of those capacitors was an inductor, you would still have two energy storage devices, and you would need two equations if they were both first order, and they would hopefully be coupled. Well, if they're decoupled, all the better. Then you have two first order equations to solve, but they would satisfy or solve your entire circuit. Did that answer your question? Yes. This is all the question is asking for. Wonderful. So don't think that, oh, I must be missing something. It couldn't be this straightforward. It might be. But yet one problem might be kind of a challenge because, oh, now I have to find the equations, I have to Laplace transform, I have to inverse Laplace transform. What in the world? But you need that to solve it. So there are different levels of complexity potentially on this exam. Who's next, or who hasn't? Back row. So look after the number, but I think they'll all be weighted the same. So even though the problems are not equally difficult, they may be equally weighted. So you'll want to plan your time accordingly. Just like if you haven't gotten to problems 7, 8, 9, and 10, you might want to think about doing those, hint, hint, that I tried to say on exam 1. So look through the exam and see if there's some that just jump off the page and you can immediately solve those. Question?
So for this example, you could have done a KCL at A and then done a KVL.
Yes. You have two equations, but they have to be independent. They have to be linearly independent equations. You couldn't have two equations that had exactly the same information in them. And so by doing a KCL at A and a KVL around the second mesh, those are different relationships, so those would be okay. And that's why typically when you do the mesh analysis, you automatically have that independence because you're writing an equation for each of the meshes. When you do node voltage, you have independent equations because you're looking at the individual nodes or distinct nodes when you're writing those KCL equations. Now we are finished, aren't we? No? With this one? There's other ways to solve this, and you can see that in the solutions if you want. Let's look at 3. Now I'm asking you to Laplace transform. Yes, you do not need to simplify your answer.
Can we do ladder?
No. Can you do the ladder on this? You can try, but you won't get any points for it because there's no circuit to perform a ladder analysis on. I've already given you the circuit. You now need to Laplace transform. So there's no ladder to scale on this one. Big laugh from the audience. No laugh. Ha ha. Now, what I've been finding is that some of you are getting hung up on when you have a term like this. Let's just say that I have e to the minus 6t u of t, and I want to take the Laplace transform of that. Some of you are wanting to Laplace transform this and then Laplace transform that and multiply them together. No, 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 no. Don't do that, please. This is really just e to the minus 6t for t greater than or equal to 0, and that's how we've defined our Laplace transform. Our Laplace transform is one-sided. People are saying, oh, I know this. This is 1 over s plus 6, and this is 1 over s. This is not correct. Is that clear? So don't be doing that when you Laplace transform and have terms like this term on the right. Now you'll never know what I just said unless you came tonight to the review session, unless you listen or watch this video. I don't know if I'm recording. I hope I am. But I'm not coming through the speakers in the classroom, so when I'm yelling, it's probably, you'll have to turn the volume down if you're listening to this recording. This one on the right isn't really that hard, is it? That's actually coming to us from this table. That's line number 2, isn't it?
From that problem, if I just wrote,
We have to have this telemetry developed, this telepathy. Let's see. I see a hypotenuse. Where did this come from? So if you write down the answer, you could say by inspection. But this is really going to probably take a couple of steps to do. Well, I mean, if you have the second derivative, you could write that down immediately. There is a formula for that. It just has a couple of initial conditions. But I would show each of the terms as you do this. So what is the Laplace transform of v double prime? Is that right? So that's the first term. Then the second term is just 5 v of s. This is fine if you write it down this way, but please show me your work. This is all that I need you to show me, though. Then what's the next one? This is a unit step, except it's delayed in time. And that delay in time says that I have the delay amount, which in this case, t naught is actually just 1. That's the last term on the left-hand side of that equality, Laplace transformed. It's 1 over s e to the minus s. And then I have the right-hand side, which you said wasn't a big deal. That's 6 over s plus 2 squared. And that's okay. There's 10 points. You've got 10 of these, so some of these have to be somewhat straightforward, right? Can we look at a not straightforward? Let's look at 4. Is 4 straightforward? Or are there questions on this, on 3? What was I trying to emphasize here? Don't start taking the product of transforms when you have that switch, u of t, on some terms. Is that clear? That's just a source. That's exciting. That's exciting this differential equation at time t equals 0. It's kicking on or turning on this 6t e to the minus 2t. What's that term doing as a function of time? 6t e to the minus 2t. Is it going unbounded with time? It has a t in it. T just blows up, doesn't it, as t gets big? But you have this decaying exponential, don't you? And that's swamping out this t that's going up. So this sort of has a bump to it, but it comes back down because e to the minus 2t starts overweighting or overpowering the t term. So that's well behaved as a function of time. That's 6t e to the minus 2t. By well behaved, I mean it's bounded. Let's look at 4. What's the big deal on this one? Or what might be of interest on this one? Now I have an exponent that's not the same as my when I'm turning this on. It's now sort of a delayed decay. Boy, are my eyes that bad? These screens. Okay, the left is a little better, isn't it? Okay. But what I'm trying to find now is I'm trying to find that these are now f of t minus t naught u of t minus t naught. Then I can immediately say, oh, this is capital F of s e to the minus t naught s. So I need to make the argument of my switch, or this unit step, look like, or the f's argument look like the argument on my unit step. And what can I do? I can also say, wait a minute, my Laplace transform is a linear operation. I can break this up into different pieces. I don't have to solve this as one piece. I have a piece on the left, and then I really have, why do you put parentheses around t minus 2? Just to maybe make you question what you're doing. But that's just t minus 2. That's 2 terms. It's a t term and a minus 2 constant term. Is that clear? Which says then that I can write this as maybe an f1 of t plus an f sub 2 of t plus an f sub 3 of t. Where the f1 of t is now e to the minus 3 t minus 1 u of t. But that, right now, the time expression in the argument of this exponent is not just t, is it? But I can rewrite that, knowing what I know about exponents. I can say, oh, that's e to the minus 3t, and it's e to the 3 u of t. Now that looks pretty good, because I know how to Laplace transform e to the minus 3t u of t. That e to the 3 is just a scaling factor. That's just a constant. That's a big number, but it's a number. So that this, when I transform this part of that whole f of t, this becomes, if I didn't have this there, what would it be? It would be that, wouldn't it? And that I have highlighted is just a scaling version, or factor. So that's the first part of that Laplace transformed expression. So now I have 3 of the 10 points. I have a third of the problem solved. Is everybody clear where that came from? Then f sub 2 is just t u of t. And that I can immediately see in my table. That's time So that's S quantity squared. And then I have F sub 3. And that's just a weighted unit step. A unit step is 1 over S. The weight on that is minus 2. And now I can just add those three pieces up and I have my answer. Questions on that? No. So the question was, would I expect you to simplify that? I would just expect you to write that as capital F of S is the combination of F sub 1 of S, which I don't remember what it was. It was too far up on the page. But it was just that. So now this would be and that's as simple as I need you to make it. Don't combine it. That makes it uglier or more challenging for me to try to see what you have. Just keep it separate. Questions on that? Do you want to see another circuit or final value or initial value? All of the above. On this one, what do you need to worry about here? Just the structure. So you don't have to find the coefficients in a partial fraction expansion. You just need to write out your partial fraction expansion in terms of unknown coefficients. And can you immediately start doing the partial fraction expansion? That's the key question that you have to keep track of. Yes and no. Okay, you can complete the square. You need to factor that s squared plus 8s plus 20, and it could have two real roots. But this one now is complex, isn't it? S squared, the quantity s plus 4 squared plus 4 squared. But what I'm asking before that was, is this strictly proper? Yes, make sure it's strictly proper before you start partial fraction expanding. This one has a second order numerator and a fourth order denominator. So here goes back to one of those earlier questions. Do we need to solve this and then find the time domain expression? But how big of a time domain expression are you looking at here? By that I'm meaning how many energy storage devices do you have? 1, right? So this is just a first order differential equation, and you should actually be able to solve those in the time domain if you wanted to. But we're doing Laplace, so we're probably wanting to Laplace transform, then inverse Laplace transform to find the resulting answer. And I'm asking you to find I sub L of t. You have a current, so are you starting to see that maybe I'm begging you to write a KCL equation? You could write two meshes. The left mesh is just I, that's given, and the right mesh you could write, I guess, in terms of I sub L. But I sub L now is a combination of I and the second mesh, and that may not be what you want. But KCL here is I of t, that's going in, and the others are going out. I have I sub L of t. So if you have inductors, what are you probably going to want to write your equations in terms of? The voltage or the current of that inductor? The current. So you probably want to find this differential equation in terms of I sub L and its derivatives. And how many derivatives are you expecting? Just one, since it's first order. Are you starting to feel comfortable with this or with that way of thinking about the problem? Then I have plus V sub R, which is the same as V sub L, over R. But that doesn't quite look like a first order differential equation, does it? We need to get rid of that V sub L, but you know how to replace that V sub L in terms of the inductor current. That's Eli coming to your rescue. Now Eli tells you that the inductor voltage is L di sub L dt. And this entire piece can go in for V sub L. And now you have an equation, I of t is equal to I sub L of t plus L over R di sub L of t dt. And if I just ask you for the governing differential equation, you would be done. But I didn't. I asked for I sub L of t as a function of time. But now you can Laplace transform this. And what was the current source? That's just a unit step weighted, isn't it? If we now Laplace transform this, I end up with 4 over s is equal to I sub L of s plus L over R times S I sub L of s minus little I sub L of 0 minus. But I'm making your problem a little bit easier because I said you have 0 initial conditions. So that initial condition right there is gone. And now I just have to replace L and R. L was 1 and R was 2. So this now becomes 1 plus 1/2 s times I sub L of s equaling 4 over s. I just combined my I sub L's. And now I can solve for capital I sub L of s. Capital I sub L of s is now 4 over s, and I'm going to divide by 1/2 s plus 1. And to make that look more like what I'm used to seeing, I could multiply the right-hand side by 1, where my 1 is just 2 over 2. What does that allow me to? Now I can say that's 8s, and I can push that 2 through this first linear factor, and the 1/2 and the 2 give me just 1. And the 1 times 2 gives me that. Now, does that look like something you can inverse Laplace transform? That should feel warm and fuzzy by this point. This now says that I have an a over s plus a b over s plus 8. And all you have to do is find a and b, and then you know that I sub L of t is a plus b e to the minus. Where did that 8 come from? Somebody's communicating wrong here. Yeah, it's probably this person right here. I'm keyed in on the wrong person. This was 2. And in this case, you could solve for a. You know how to do that. Multiply both sides by s and let S equal to 0, you now have A over S plus B S plus 2 equaling 8S S plus 2, so that A is now 8S plus 2 and B, multiply both sides by S plus 2 and evaluate at S equal to minus 2. Boy, it must be getting late in the day. And there is my I sub L of t. It's now 4 minus 4 e to the minus 2t, or I could hit that whole square bracketed piece with u of t. Yes?
We have a second derivative. We subtract, like we had I double prime t, we would subtract I L 0 and then subtract I prime 0.
If you have this, let's say that you now had v double prime of t, and you wanted to Laplace transform that, then I would say, oh, that's S times the Laplace transform of v prime of t minus v prime of 0 minus. Yes? That's just applying the derivative, or the Laplace transform of a first derivative. Now I need to get rid of that Laplace transform of v prime. But I know how to do that. I just did it. That's now S v of S minus v of 0 minus, so that now I end up with S squared v of S minus S v of 0 minus minus v prime of 0 minus. And that's the Laplace transform of a double derivative. So you do have more initial conditions that come in for each derivative that you have to have to deal with. But that's where those additional terms come from. Is that what? You don't need to show that. You were wanting to just write down your answer before, weren't you? So the question was, do we need to derive that? You don't have to derive that. You can write this down. I'm assuming that you know how to do that if given time, and you don't have time to derive it on the exam. If you forget it, if it's not on your table, derive it. You know how to derive it. It's not going to take you that much time. Initial value theorem? I don't know, can we? Oh. Number 8. Number 10. What is number 10? This says find the steady state values for the capacitor voltage and the inductor current. This is now a DC source, and it's just asking you, what does a capacitor do when excited with a DC source, and what does an inductor do when excited with a DC source? What does a capacitor do? This circuit has been in existence for an infinity of time. But you know in electrical and computer engineering, how long is an infinity? 5 time constants. So it doesn't have to be energized for very long, and it's reached steady state conditions. And that's all you're asking. But what happens when you have DC sources applied to capacitors and inductors? This is, I think, what we started with in the topics list. The capacitor's open and the inductor's short. So that now you could immediately redraw this circuit and you could say, oh, I have a resistor and my capacitor is opened. That inductor shorts. This is now 3, this is 2, this is 1. Here is, did I just say limiting value? So I could call that V sub C of infinity, and this is I sub infinity. Oh, I didn't even label that with a subscript. I just called it V. And now you're just trying to find those two unknowns. What is, and now you can do Dr. Marsland's KVL across an air gap, right? To find V of infinity. Just do a KVL right here. And if you want this current, what's the current going here? There's no current going there because it's open, so you really just have one mesh equation if you need to do it to find I. You have 10 volts dropped across 5 ohms.
That question seems like it came from 220 and yeah.
And I did what?
But you needed an extra question to throw in there.
Well, I did, basically. I'm just asking, can you find initial conditions? This could be the way a circuit is set up before t equals 0, and then at t equals 0, you switch it, and you need to find the solution after t equals 0. Yes, I'm basically saying, can you rework a 220 problem? It's exactly what this is. Questions? Yes? So is there any way to use the final value theorem on this? You could, if you found, let's say that you just said, I'm going to solve this generically. Let me say this is now V sub 1 of t as an unknown voltage. You could now find the differential equations. What would the differential equations governing this circuit be? How would you solve that if that voltage source is now a generic source that's V sub 1 of t? You would do a node voltage. How big of a differential equation are you expecting? What's the order? Second order, aren't you? So now if you just did a KCL at that top node, are you done? Possibly not. So now it depends on what you're writing, but you could write 2 KCL equations. You could write 2 mesh equations, but that's what you would need in order to solve the differential equation for this. You could Laplace transform that and then use the final value theorem. That's overkill for this problem. But that's good exercise if you wanted to do that. Not on the exam. I wouldn't take the time to do that on this exam. But if you were sitting around and you were playing exchanged problems with your buddy, you might say, here, solve this in the time domain, and assume that voltage source is a generic voltage. And then we're going to really have fun. We'll look at different V1s. First, we'll give you a decaying exponential. Then we'll give you a sinusoid. Then we'll give you an exponentially damped sinusoid. But you could do all of that once you've solved this once. Now you would just have to Laplace transform different V1s of t's and plug those in and solve the resulting equation. Do we want to do any of these? Can we do the initial value theorem? What am I looking for? Now you could just say, oh, the limit as s goes to infinity of Sx of s and now what you want to do is you want to key in on the highest power, the coefficients of the highest powers of s. And now what's your numerator? It's a second order. What's your denominator? Second order and the highest. So those numerator and denominator are going to get large at the same rate, and they'll be scaled by whatever the coefficients preceding that highest power have for their scaling. The numerator is going as 4s squared. The denominator is going as 2s squared. The s squareds are moving exactly the same as we go to infinity. They cancel, and we have 4 over 2. That limit exists. We can apply it, and that's now our answer. Is it clear where that came from? What about the bottom one? Can we apply the final value theorem? Now we need to look at s y of s. This is now 10s over, and I might look at my terms and see if anything that first term can be rewritten. And now I'm looking at this to see, are the poles of this expression okay? And by okay, what do I mean? Are all of those values of s that cause my denominator to equal 0, are they all in the strict left half plane? They can't be on the imaginary axis. It can't be at 0. We've canceled one of those at 0. That's okay. But if you started with something else, suppose that you now had y1 of s, that was 10s squared s plus 2. Could you apply the final value theorem for y sub 1? Because now you're looking at this, and do you have any poles on the imaginary axis or in the right half plane in this sy sub 1 expression? You do. You cannot apply this y sub 1, if you inverse Laplace transformed, is going to have a t term in it. It's going to go unbounded with time. It doesn't have a final value. This y of s is okay. It has one pole at the origin, one right at the origin, but that's okay because it's getting canceled by that s. Here we are taking the limit as s goes to, this is the final value theorem, what are we letting s go to? 0. And now in here I have the limit as s goes to 0. I have 10 upstairs. I have a 5 and a 2 downstairs. I'm going to 1. This is now y of infinity. Questions on that? What if I had a y sub 2 Can I apply the final value theorem to that? I have one pole at the origin. That's okay. But I have what? I have an oscillator, don't I? I have purely imaginary roots for the second factor. I have poles at plus and minus J2. Those are just going to sit there and bounce back and forth. Am I ever going to see a limit, a final value? No. It's just going to sit there and shake. It's never going to approach it's bounded, but it never hits it never reaches a final value. I cannot apply the final value theorem to y sub 2 of s. Question? Yes, so now you need to justify, you can say, cannot apply the final value theorem because I have roots at plus and minus J2. The final value, or the final value for y sub 2 of t does not exist because I have poles on the imaginary axis. Something to that effect. Are there Do we understand what this question is asking? If it's clear enough to read, if it's not too fuzzy. Now we have to Laplace transform this to get an expression for capital X of S and then apply the final value theorem. Which means that you need to determine, once you've Laplace transformed, you need to still check, is this an okay expression to use the final value theorem on? Now, if we didn't have any initial conditions, what would this system or equation be doing? If we had 0 initial conditions, and this is our governing differential equation, what's the solution? Do we have a forcing term? No, we have no forcing term, we have no initial conditions. What's exciting this circuit? This circuit is not getting excited. So what happens in an unexcited circuit? It's boring. If it's boring, what does that mean? Okay, if I have a midlife, well, maybe that wasn't directed at me. So I'll make that assumption. This circuit is having a midlife crisis, which means what? It's not very excited. What's x of t as a function of time? 0. I had to put in some initial conditions that are non-zero in order for this to even be valid very interesting as a question. But if I had something else, maybe if I had this, then you could talk about maybe a final value. But then it's going to be a mess because that has a pole at the origin if you work through it. And then I'm going to have 2 poles at the origin, and will it have a final value theorem? Or can you apply the final value theorem? No, it's going to go unbounded with time. I think you can look at the solutions. I think everybody's having their own crisis at this point. Are there questions? Do you have any last minute questions? We will have lecture tomorrow. I know, maybe we should just dismiss it, after tonight. But we'll figure out where we're going. You didn't hear that. We will meet tomorrow. Are there any last minute questions? If you have them, let me know. I have office hours between now and the exam.